for the great opportunity to speak. So yeah, I want to tell you, like, oh, yeah, I'm gonna forget if I don't do this right now. So everything I'm gonna say is joint work in progress with David Rader, and David Rader, and also a lot of it has been very, I think, very influenced by conversations with Constantine. So, so what I want to do is I think the way I wanted to structure this talk is just I'm going to do a sort of series of exercises and pattern will emerge. And my goal will be to sort of get close to listing all the semi-simple n categories. And maybe n's not going to be like. So here's maybe the first example you could do. This is one that I think probably everybody here can just do in real time with me. Let's list all the semi-simple one categories. Semi-simple one categories. And maybe I'm over a field, and maybe I'm going to assume I'm characteristic 0. So what you do, you pick up a category, and you pick up a semi-simple category, and you go and walk through its objects, and maybe you pick one simple object of each isomorphism class. So you can immediately write your category as some sum, maybe it's index, whatever, there's some finite set. And then you might write it as some sum of simple categories. And then you could ask yourself, what's a simple category? So a simple category has some ring attached to it, which is the sort of endomorphisms of the unit of any chosen simple object. So up to isomorphism, these are classified by division rings over K. Well, how do you classify division ring? I'm doing this in a very sort of roundabout way to give a flavor of how things go. How do you classify division rings? Well, a division ring has a center. I think D is a good name for whatever. A division ring has a center, maybe something like that. So what do you do when you want to classify division rings? You look at the center of A. That's going to be some field, sort of some field extension. Okay, and then to tell you the actual division ring is probably to tell you like a Brouwer class over. And this is a sort of convoluted way to say the following. So what you really should do to organize these data, regretting the word, okay, so to organize these data, here's a better thing you could do. You could look at, following very silly thing, you could look at the spectrum of your field. So that's just a sort of heavy point. And so you could look at this is, I wish I didn't have this set. Here's the difference. Anyway, you could look at the spectrum of that, look at the sort of the spectrum over the algebraic closure. So what am I saying? What is a field over a perfect, what is a perfect field? What is a separable field extension? It's just a finite set with a transitive Galois action. That's what I'm trying to say. So this is, of course, the same as a finite set with a transitive Galois action. And now I could already short circuit the fact that here's a set that I've broken up as a bunch of transitive Galois actions. Well, that was a silly way to do it. I should have just said I had a set with a Galois action and not a disjoint union of transitive Galois actions. And so this whole data here of the finite set with the transitive, with a bunch of orbits, this is the same as some set. This is why I wish I hadn't called this X. A finite set with a Galois action. And then what's the data of a Brouwer class? By the way, what is this set with a Galois action? This is something you already knew. This is what you would have gotten if you had looked at this is sort of some of the data. You can read it off completely canonically from the category because this is sort of the spectrum, if you will, of the natural transformations of the identity functor on C. That's who that set is. That's something completely canonical from a category that I can write down. And then the rest of the data of the Brouwer class, who is this? This is some cohomology data, right? A Brouwer class on a field is just classified by Galois cohomology. And so these Brouwer classes are together function. What are they? They are a class function, a Galois equivariant function class. Sort of, however you want to say that. It's an H2 class on your set. H2 class on the quotient of your set diagram. So
what is the block here?
I mean, I mean the following. I mean that let me say. I'm saying that what I'd like to say is the following. What I really mean is, if I just had an ordinary field and I asked you for a Brouwer class on that field, you would say that's an H2. The division ring itself for a fixed. If I want to tell you a central simple algebra, is to tell you a class in. I would sort of probably write it as like H2 of the field with coefficients in the multiplicative.
That would be really the group homology of the Galois group.
That's really the group cohomology of the Galois group. That's literally the group cohomology of the Galois group. And so what I'm saying is I'm just saying you take, if I want to assemble all the data together, the data of the category is the same as the data of this finite set. It's a finite set with a Galois action, and the data of a class in the sort of the Galois equivariant cohomology. That's
When it is second, it's like you're getting rid of X, right? It's this, so you have X.
Yeah, I mean, this is a very, just a sort of packaging of these data.
Just the name.
I haven't done anything. This is, there's nothing deep here. A set with a group action is the same, like, if I like the course, rather this is really just something about the quotient groupoid, and that groupoid just breaks as a disjoint union of orbits, each of which looks like a BG, and then it's just group cohomology with. And the only interesting thing is that I have twisted coefficients. But you know, this is sort of, okay, so is this good or is this useful or not? Well, it's as useful or not as you understand the Galois group of a field. Of course, in a random field you probably don't know anything about its Galois group, but if you pretended that you understood how to compute Galois groups, then you also understand how to get the space of semisimple 2 categories or semisimple 1 categories. So I wanted to do this because there's a slightly better, maybe better, I don't know. So the reason why this works, at the end of the day is the following. So see, whereas like David this morning had like thought his entire board workout ahead of time, I have thought none of my board workout. So the reason why this works is the following. Let me start giving some notation for things. I'm going to write a curly V one for the category of vector spaces field. So who is that? That's the category of finite. I just mean finite dimensional vector spaces. I don't know what an infinite dimensional vector space is. The finite dimensional modules of my field. And let me write V2 for the category of finite semisimple 1 categories. So this is the finite dimensional modules. Finite dimensional module categories over V1. But this is just, I guess this was a theorem of Ulrike Tillman. This is the exactly the semi-simple one categories. And now you see what, if I write V7, you know what I mean. Because you just up the 2 to 7.
What does finite dimensional mean?
There we go. It probably means fully dualizable instead of finite dimensional. And I mean this sort of in the naivest world you could mean it in. So the reason why this game worked, why it broke down to just a classification in GM, what did I really do? What I really did was I did the following. I said, let me temporarily step over the algebraic closure of my field. And I'll just try to do the classification over the algebraic closure first, and then I'll finish the problem by Galois. And then I said over the algebraic closure, I could try to write my, I should even put this in. So why this works? Well, step 0 is some sort of Galois descent nonsense. And then the rest of the argument is you look over the algebraic closure, you do the problem on the algebraic closure, and on the algebraic closure, you write every category as a sum. So that once you're at the algebraic closure, you write this as a sum of invertibles. And so you had to prove a theorem that said that every category was written as a sum of it, decomposes canonically as a sum of invertibles. And now you have to classify the invertibles, and the invertibles you know how to classify very easily. Invertibles in, so where are these? These are invertibles in this category sort of B2, but over the algebraic closure. B2 minimum. Algebraic closed invertibles. And this, of course, you know, is just a, this is a group that looks like, so you had to prove that sort of there's only one, there's no homotopy in degree 0, there's no homotopy in degree 1, and there's there's an invertible number worth of homotopy in degree 2. You see this is in degree 2, which is the same as this 2. So let me do this same exercise again. Okay, that was a good exercise. Let me try to write down all the, maybe I don't like categories. Maybe I really want, say, categories with sort of super categories. So let's try to do all the categories, all the 1 categories, which are you know, finite semi-simple, and elements of super categories. This means that it's tensored and enriched. Over super vector spaces. It'll be sufficiently nice for me to give a name for super vector spaces. So maybe I'm going to give some more names. So the letter after V is W. So I'm going to write, so this pattern continued, by the way. 0 was, it's just my field. So let me write, let me not give the name yet. So, and then I'll explain why I actually care about this question. So you could walk through exactly the same argument.
May I ask a question?
Say, maybe
May I ask a question?
Just do the problem. So you do some sort of argument about Galois descent, and then you decide to work over an algebraically closed field of characteristic 0. And then you have to classify invertibles, and then you have to show that, so you have the same thing, you know how you want to decompose your category. So what you want to decompose your category as sum indexed by the spectrum of the, so you decide to decompose decompose your super category as a sum indexed by this algebra. And now you're going to complain, hey, I'm in super world. This is a perfectly good commutative algebra, but it's a super algebra. What do I mean by spectrum and indexing sums? And I'm going to say I'm semi-simple, and a commutative semi-simple super algebra is just a set. So you still try to decompose it by some index by this, and you have to prove, I didn't even number my numbers. 0 and 1 wasn't very many numbers. And then you have to prove, so you can do this, you check that you argue that each summand is invertible. And that's not very hard to argue. Let me do it for you. So each summand has so what do I have to do? I have a summand who's with the, all I have to do now is think about categories for which the endomorphisms, the identity, there's no endomorphism identity. So for which that looks like a point. So I just sort of have to think through those cases. There are 2 of those cases now. And then I have to classify. Invertibles. The classification of invertibles in the super world is probably something I hope many of you have seen before in some names. So there's still k many in sort of at the, so there's 2 isomorphism classes. Super categories. They correspond to the 2 division rings. Think of this as like cliff 0 and cliff 1. And of course, pi 1 is the number of super lines. That's also a Z2. And so, well, I haven't quite told you this full spectrum of invertibles. Now I really want some notes. So I'm going to start, using the following notation. So I've already sort of thrown up boldface GM. If I have anything at all, I'll just write GM of it to mean the invertibles. So this I'm going to call this, write this as GM of whatever the category of supercategories is. Finite semisimple supercategories.
Okay, sorry, basic question. What are these homotopies of?
These are the homotopy groups of the set of invertibles. It's of this. You take the category of supercategories, which is to say the category of categories tensored and enriched over supervector spaces. This is a monoidal category because you can tensor over supervector spaces, this sort of relative Deligne tensor product on these. And so you can ask, what are the invertible objects and invertible morphisms between invertible objects? And if you work out what is the set of, what is the space of invertible objects, up to isomorphism, there's precisely 2 invertible objects if I'm over an algebraically closed characteristic 0 field. And they have names. They're like modules for cliff 0 and modules for cliff 1, potential names. Same thing I did over here, where if I have a simple object, I could name it by a division ring. If I have a simple object, I could name it by a division superalgebra. And now you could ask, what are so that's the sort of up to isomorphism, that's pi 0 of this space. You could ask, what are up to isomorphism, the automorphisms of an object? So the super lines, so that there's 2 of those, the even line and the odd line. And 2 is k cross.
Tero, may I ask a question?
Please.
Yeah, so maybe it's a comment that so you said that this V1 is vector spaces, so there is exactly 1 object for each n dimension, and this corresponds to Hilbert theorem 90 that H1 of Galois group with coefficients in GM equals to 1, right?
Yes.
Mhm.
That's right. I mean, I didn't actually use Hilbert theorem 90. I used, except for the case when my Galois group was trivial. So I did, when I, in my classification, I did use that there were, that over the algebraic closure of K, there's nothing in degree 1.
Yeah, no, but I mean for V1, that V1 is vector spaces, so not very many cases, and this corresponds to, because I suppose V1 is classified by H1, yes?
Yes. I mean, V1 is vector, I mean, I don't know where you want to think of the definition versus the theorem. So you know from the existence of basis, there's not very many invertible vector spaces.
Right. And this, and this is exactly,
that's a Galois problem.
so it's interpretation of Hilbert theorem 90.
Yeah.
Mm-hmm.
So I'm not supposed to stand right here. It says so. So I want to make a couple comments about this. There was a reason I was saying all this. So as I said, I want to give a bit more useful notation, or I think it's a useful notation. Maybe useful notation, which is that the letter after V is W. So I'm going to write W0 for the algebraic closure of K. And one reason to think about, and I'll come back to this in a moment. I'm going to write W1 for supervector spaces. Categories. And we'll come back to that in a moment. And so what am I saying? This group here, this was, well, as I said, this was GM of supercategories. It's GM. And I haven't quite told you this space. So what you will find just from repeating this argument is you will find that now you could actually do it sort of over anything at all. So you'll find that if you wanted some other problem that you had, maybe you had some other field and you wanted to do super categories over some other field, for instance. If you wanted to classify super categories over some field, you would sort of take the classification. You would say, oh, a super category over some field is going to be a finite set with a Galois action computed just from this endomorphism algebra. And then instead of an H2 class with coefficients in GM, you'd have some more interesting cohomology data on it. And the more interesting cohomology data, so what you find is that semisimple, so for example, you the following type of theorem, you find that possibly supercategories, finite semisimple supercategories, over now maybe not an algebraically closed field, are classified by, well, again, a set the Galois action. And now a class, a Galois equivariant class, in whatever the cohomology problem that this higher groupoid is classified. In whatever, in sort of, whatever this GM of W2 cohomology is. So let me say a few words about this cohomology theory. So I did not tell you the full cohomology theory yet. I only told you the homotopy groups of this space. And to tell you a cohomology theory, I have to tell you more. In particular, there's possibly hidden extension information, connective tissue. And maybe might be easy or hard in any specific problem to work out what those data are and what I need to do to tell you about. So I don't know, maybe I start my life without knowing very much. All I know maybe are that list of homotopy groups. And I want to figure out which cohomology which spectrum I have with this list of homotopy. So what do I know? I know I have, so I've decided to care about we have some as yet mysterious object calling GM of W2. And where does it live? It lives in the kind of E infinity symmetric monoidal, whatever you want to call it, it's E infinity sort of two group ones. Group like E infinity two group points. That's where this object lives. And I don't know very much about it. I do know that what its pi2 is. And so I could ask sort of what are it's so I know that it's an E infinity groupoid with prescribed pi2. And I can ask what's the category of all such groupoids look like? And if I'm really lucky, super vector spaces are so magical, maybe this will be some specific favorite object in this category. So it turns out, I'm just gonna tell you some facts. So it turns out that the category of all of these, I should have chosen a name ahead of time. So category of these as an initial object. Which of course is just has k cross in degree 2 and nothing below it. You might call it, I don't know, H2 with coefficients in k cross, if you want. Okay. And it almost has a terminal object. So the non-trivial statement is that it almost has a terminal object. So it turns out that at least the homotopy category of this infinity category has a terminal object. It's a non-trivial statement. It's not true if you changed k cross bar to something else. To know that this has a terminal object, this would be true for any group here that was a divisible group. This is not due to me. This is called this terminal object has a name, and it's called the Brown-Kamenetz stool, or the spheres. So it has a name, and the letter after H is I, so I'm going to call this I.
The fact that you're stating as in the homotopy category, I'm curious, you know that it is not true for the full infinity category?
Yes. Already at this level, it's not true.
Are there automorphisms of that?
This thing has automorphisms.
Yeah.
This thing definitely has automorphisms that are the identity on pi2.
You know a lift of that to the category, but it's not a terminal object there.
Well, I mean, I don't know it. Brown and Kamenetz and Anderson know it. And even better than being a terminal object, you can actually characterize this object among all, might be equivalent to what I just said. If you look at all symmetric monoidal 2 groups, so if you look at the category of group like symmetric monoidal 2 groupoids, and you pick some random group there, then what you know is that you know what the homotopy maps, classes of maps into this are. So maps from A, this dual object, homotopy classes of maps is just subabelian groups. That's pi 0. space. So there's the full sort of who this object is in the homotopy category of groups, of abelian 2 groups, abelian 3 groups, whatever the correct numbering is. So in particular, I have an object in this category. And oh, so actually, let me say this even better. I can drop all these words group like and so it doesn't have to be a 2 groupoid. This was true for infinity groupoids. It's always maps from pi 2 in this case. This 2 is this 2. And so from testing against suspensions of the sphere, you can compute the other homotopy groups. And so anyway, so what you can do, so you can, for instance, can compute by 1 and by 0. And they're just the dual groups. So the dual groups to pi 1 of the sphere spectrum and pi 2 sphere spectrum. A cross dual groups, because they're just given by maps of K cross. And hey, these are both Z2s. And these are both Z2s. And so this invites the following question, and it strongly suggests, and then you actually go and check. This was the terminal object in this category, at least up to sort of homotopy is the terminal object. And so I just have a canonical map, which is given by the identity on K cross. So you get a canonical map. Canonical up to higher homotopy map from GM of W2 to I2 of K cross. And now you just have to do a computation. You just have to compute this map, but you don't have to compute very much. You can compute this map is an ISO on pi 1 and pi 0. And you do have to actually compute that if you're doing it this way. And therefore an ISO.
Would that have been K bar cross up there?
Probably. Yeah, it was not true. If it was just a K, then there would be more pi. Then this was already false. If I was just working over a random field, there'd be more division rings. And also this terminal object probably doesn't exist without a bar, because I do need this to be a divisible group for this terminal object to exist. So, so it's an ISO. So actually, we even have a name for this cohomology. It's always nice to have a name. You know, this was somewhere in Genesis. You go out and you give names to all the animals and therefore control them. And so I've given a name to this. So now I feel like I control this cohomology problem. So the punchline is that supercategories are classified by sort of I cohomology set with an equivariant I cohomology class. So why did I switch games to supercategories? Well, for the same reason as I switched to, as I liked to work with the algebraic closure of a field rather than a field that's than the original field. Because, and this is why I started writing W for an algebraic closure, but then superalgebras. So a ring is algebraically closed, is a definition, maybe or a theorem. Pavel can tell me which of Hilbert's theorems this is. A ring is algebraically closed. This is called Hilbert's Nullstellensatz Satz. A ring is an algebraically closed field algebraically closed field. If for any, let me just say sort of non-zero and sufficiently finite. And the art is to figure out what sufficiently finite means, because otherwise this is a vacuous statement. For any non-zero and sufficiently finite ring map, there should exist a splitting. Hilbert says that characterizes fields modulo the fact that I didn't tell you what sufficiently finite meant. In fact, you can use lots of different definitions of sufficiently finite and they all work. But there's some art, because if you're either too strong a notion of sufficiently finite or too weak a notion of sufficiently finite, then it won't be true. For instance, maybe sufficiently finite means for you only the isomorphisms count as sufficiently finite. That'd be a silly definition. Those are, being an isomorphism is a very strong finiteness condition. And then this is not a good. So, so around 100 years later, Tolene proved the following. For every non-zero and then sufficiently finite. Sufficiently finite. Symmetric monoidal category map. From that's with domain SFEC has a splitting. This is, as I said, this is called Schnellensatz. And this is called existence of fiber functors. So fiber functors. And again, the art's in figuring out what sufficiently finite means, and I'm not going to do that in real time. And so if you just look at these two theorems, you should immediately say, oh, that means that SFEC is algebraically closed. And the point is that this theorem, it was not true for vector spaces. So the map from vec to SFEC, you will be hard pressed to convince me that's not a very finite map. There's definitely a functor from vector spaces to supervector spaces. And in characteristic not 2, I don't know, in characteristic 2, who knows what finite means, but in characteristic 0, supervector spaces is a nice kind of separable fusion category over vector spaces. Those are definitely sufficiently finite, and that functor does not split as a symmetric monoidal map. And so vec is not algebraically closed, but supervec is. And so that's why I'm calling supervector spaces W, because
one characteristic it would be in the category. Right?
That's right. So if sufficiently finite means fusion, yes, then these are the Verlinde categories. If sufficiently finite means, well, then the Verlinde categories are examples of algebraically closed categories. If sufficiently finite meant separable fusion, then even in odd characteristic, supervector space is already closed for separable extensions. So as I said, there's an art in deciding what sufficiently finite is. Characteristic 0 makes it easier because some of the questions about separability versus semi-simplicity I can ignore. So.
Sorry, I'm sufficiently finite. Is that just a condition on the map, or does that include a condition on S?
Yes. So, as I said, there's an art to deciding what sufficiently finite means, and I just want to not talk about it in this talk. But a priori, it's a condition on everything. So, okay, so I have 10 minutes. Is that how long I have? Okay, great. So now for the main part of my talk. So it was not a surprise that this had an sort of that there was an algebraic lit. So it turns out this is not actually a suppressed. So what we've proven with David is the following. So I'm not going to, okay, an algebraic closure, of course, is an algebraically closed thing, which is sort of an inductive limit of sufficiently finite things. And what we've shown with David is that that there exists a category W for every n. So every n, there's a category called that we call Wn, which is the algebraic closure of, really, I mean the separable algebraic closure of Vn, and that Wn is characterized by the following furthermore, Wn is the unique category, unique symmetric monoidal n category, following features. First of all, it should be, well, it's a slightly infinite object because algebraic closures are always slightly infinite objects. You have to take inductive limits, but it's an inductive limit of finite semi-simple extensions, finite semi-simple categories, and it should have, well, I already told you what should go on in degree 1. That super vector spaces is a degree 1. So that's sort of forced by algebraic closedness. And the other thing that's forced by algebraic closedness, so if you're algebraically closed, then in particular, you have all roots of unity. So in particular, you know who the roots of unity are. That's like the type of thing that, so, and if you want to say it in this language in terms of Null-Stonsatz problems, you could say it in terms of testing, not against arbitrary ring extensions, but just testing against group algebras for finite groups. If the only rings you know about are group algebras for finite groups, you know what the roots of unity are, if that's the type of test you can do. So just from testing against group algebras in a higher sense, you can show the following is necessary, and our theorem is it's sufficient. Is that also that the multiplicative group Wn is the version of this Brown commanded stool. Full stop. That characterizes the algebraically closed field. And so now I have 5 minutes. I can tell you half of, so I have to change my, can I rewind and change my title to half the semi-simple categories? Okay. So what we have understood is a complete list. I told you a complete list of objects. And so this means that if you have any category at all that you care about, if it's sort of finite over vec, then it'll have the same algebraic closure because, you know, if you do a finite extension of a field, you haven't changed its algebraic closure. And so for any reasonable category, if you want to know sort of questions about its higher representations, you could in principle pack them using kind of by studying the corresponding question over W and then doing a Galois assembly. So now let me tell you sort of all the objects of W, and I only want to do this, I think, in even degree. And then I'll have like negative 10 minutes left and I'll tell you the odd. So I'm going to give you an exact list of objects in the same way that the previous one, it was really an equivalence of spaces. The space of semi-simple 1 categories was the space of finite sets with a Galois action and some equivalent cohomology data. So I'll just tell you the sort of the formula to go between the spaces. So given a category, given an object in W2n, so this is some type of n-1 category. So what I can do is I can look at, I can look at the endomorphisms of that category. And then I can look at the sort of endomorphism of the identity functor of that. So that's sort of the loop space of that endomorphism algebra. And then I can loop that a bunch of times. So loops n means endomorphisms of the unit.
Just to be clear, you mean n, not 2n there?
I mean n. Okay. Yeah, so that's this is a 2n, this is an n. So here, what do I have? I have n many monodalities from the loopings plus 1. So this is an n plus 1 category. So this is n plus 1 monoidal. And C started out as like an n minus 1 category.
2n minus 1.
2n minus 1 category. And so this was 2n minus 1, and then I'm subtracting off another n. So this whole thing is an n plus 1 monoidal n minus 1 category. Or of that category number. I mean, it's not a category, it's an element of W, but it has the category number of an n plus 1 monoidal n minus 1 category. And so it's a commutative algebra. So it's the infinity. And so it has a spectrum, which is
Stabilization, right?
yes. So this is a stabilization hypothesis. And so there's something that I could call spec of this category, which is defined as in whatever E infinity W out objects from this thing. That's a W, whatever. So that's some space. This is some finite n minus 1 type. And C will definitely decompose as, let me give this a name, I'm gonna call this X, will always decompose as in some sort of, as an integral indexed by this category. And these objects, this is where I use that I'm in dimension, in this dimension statement.
So do you really have an integral or is it finite something?
It's a pi finite space.
Well, I mean, the integral.
Yeah.
You assume all the finiteness at every step, do it?
Yes.
Then it'll be just a finite thing.
It will be,
Yes. Oh, okay.
I'm in,
Yeah, X is whatever.
X is a pi finite space. This integral is sort of in the sense of Ilary or Schlank et al. On kind of semi-additivity. And the claim is that each X, so I should say this better. So the point is the following. So each CX will have sort of a spectrum of a point. So the same algebra for each of these fibers. So what am I doing? I'm basically taking, you like to do this in general, you like to take a space and maybe with a commutative algebra living inside, you'd like to take an algebra. If you have an algebra with a commutative algebra living inside of it, you're very tempted to try to decompose your algebra over respect of that commutative subalgebra. And that's what I've done. I've taken my object, I have a representation of some commutative algebra living inside the endomorphisms, and I'm just decomposing my object as a direct integral over spectrum of the, sorry?
Blocks. Yeah,
That's
representation too.
exactly. And so the statement is that each fiber is really like a factor. It's like trivial endomorphisms. And here I'm again going to use, so once I use the 2n was exactly twice n to sort of, I'm really sharp. I don't have any wiggle room. I have n plus 1 monoidal n minus 1 category has no wiggle room. Like that is the infinity, but if I tried to make those any closer, I wouldn't. And my claim is, I'll just have to claim this as a claim. My claim is that again, because I have no wiggle room, if I'm of dimension, if I'm sort of living in dimension 2n with the feature that my n many loops is trivial, then this it forces C to be invertible. And what's secretly going on here is that there's a sort of Pontryagin duality between Poincare duality, sorry, Poincare duality on the endomorphism. But knowing the sort of top half of the endomorphisms tells me the bottom half. And so what you find is that the objects of W2N are precisely the space of I finite n-1 type. From one class. What I was going to do was tell you the interesting part of the story, which is an odd degree, but I think I'm out of time. So.
Are there any question, comment? Yeah.
Before you had a set, you had a Galois action and a class for that Galois action.
Yeah.
You have a Galois action going on here, like you have a higher analog of a set, which is a pi finite and minus
Right.
one type, but where's the
Right.
Galois?
So in particular, if you ask me sort of what are objects of say V, sort of some other category that you cared about,
Oh, right.
then I would say these
there from
are
the sense.
sort of these things plus whatever the Galois group of W over V is. But, you know, I've hidden all the interesting part. That will is. Well, first of all, I probably just replace n by bullet, and then this is just some sort of group object, and like it's an infinity group. It's a group object in the infinity category of spaces. I should say we actually know the homotopy groups of this group exactly. Even a modulo of the fact that I don't know the 0th degree, but
You still assume that V is algebraically close to.
that's right. So V is algebraically closed, then I know the homotopy. If I start with an algebraically closed field, then know the homotopy groups of this guy. I know even more than that. I know how to stick it inside of a fiber sequence. I mean, by I mean it's like I can write this space in a fiber sequence with the homotopy groups of sphere, with the sort of sphere spectrum. And I can compute its the fiber of that map. And so to the extent that you can tell me what the homotopy groups of spheres are, I can tell you what the homotopy groups of this object are. But that's about the limit of what I can compute. Any question?
Could you indicate the odd dimension, please?
If the chair lets me. 5 minutes for questions. Yes, so what I did here was I picked a space, so I could run this in the other direction. And I said, look, I have a space. If I take any space and any invertible, any gerb on the space, I can look at the global sections of that gerb. And my theorem is that if I just run over n-1 types, I exactly get a complete list of objects in that category. But nobody stops me from writing down this formula for a non-n-1 type. And so a typical thing you could have done is, for example, you could have looked at say, somebody's concentrated in degree n. So you could have looked at, you could have done the following. You could have started life with somebody specifically in degree n and some class on that, and then you would get this sort of object 2n, which is not what I want. I want an object in wn. This is a thing I could do, and this is somehow redundant with my list. There must have been some lower space that knew this object. A better thing I could do is if I didn't use if I asked it to be, write I twiddle to mean that the twiddle means that it's in reduced cohomology. So that if you have a value to the base point, you get the value. This is a pointed space, so I might as well have used reduced cohomology. Now, this is the sections of some gerb over this space. there's a favorite section called the skyscraper at a point. The trivial at a point. So I get some section of this. And if I can arrange that this guy is trivial, then I will have actually given you somebody in W2n minus 1. And so if I can arrange this guy to be trivial, I'll get an element of the odd degree case. And the calculation we did with David is that this group is the isomorphic to, I'll just tell you pi 0, sort of the homotopy group. So so I can tell you the list, the sort of pi 0 of this space is precisely the sort of symmetric or skew symmetric bilinear forms on A. It's precisely the skew to the n-symmetric bilinear forms on A. And this guy's invertible, this integral ends up being invertible if and only if the form is non-degenerate. And so there's some map from groups with a symmetric bilinear with a non-degenerate symmetric bilinear form to invertible objects, and you can take the fiber of that map. And the statement is that if n is big enough, so if n is at least 2, then this map from finite abelian groups with non-degenerate class in twiddle 2n a plus take there's some map to invertibles B2n. This is a sort of Gauss sum map. So you should think of that map. And that's not the theorem. That's what I just told you. The theorem is that I told you that you can take the fiber of this map. I told you that the fiber of this map maps to the objects of W2n minus 1. And the theorem is that if n is at least 2, then this is an iso. It's the list, okay. I did the whole talk.
They're not necessarily negotiable, they're just objects.
This is a complete list of objects.
They're not necessarily negotiable.
That's right.
From the fiber.
So the point was there is an invertible thing, which is the sections of this gerb is invertible when the gerb has enough non-degenerate, so when it's classified by non-degenerate bilinear form. But I also have an element of a skyscraper sheaf at that.
F's are only the ones where the spec that you've computed before is trivial. So a priori, you also have a pi finite n minus something type in the game as well.
Ah, that's right. Sorry, you're totally right. I lied. This is not an iso. You're completely right. I totally said it wrong. Thank you. I totally said it wrong. The theorem is not that this is an iso. The theorem is, so this is what I told you is I have all of this, which means in particular, given any, more generally, given any n minus 2 type and the map next to I ran out of letters or something like that. Then I can write down. So I told you sort of what did I tell you? I told you if you're in the fiber of this Gauss sum map, then you get the trivial object with an element of that object. So that's some of the objects in Wn minus 1 and 2n minus 1. And then I could also more generally kind of take families of those. And this will be this one as well. And this is the theorem, this is isomorphic. So that's the complete list of options. Sorry. Okay, I'm told I have to leave the stage.
So maybe we can continue this discussion, during the break, so let's see you again. Usually we have an half an hour break. We start again at
So, no,